So I'm Brad. I'm one of the Kiwis that work on Faucet, and today we're going to talk a little bit about stacking. So stacking for those who haven't heard about it, but you probably have, considering all the talks yesterday used it. Well, this talk is going to explain what it actually means, because what we find is stacking has a lot of connotations which come along with that name, and it confuses a lot of people when we talk about Faucet stacking. So now we've tried for about a year to think of a different name for it, but we haven't really come up with anything better. But the basic way to think about it is, so the first initial version of Faucet we called like work standalone. So it was kind of independent. It's sort of a more traditional model. Every switch made its own decision about how to learn, how to route, that kind of thing. But now we have this kind of stacked mode, which you might know as in other controllers as a fabric, or it's like a distributed sort of setup. So we're going to talk about stack today. It's a new thing, sort of. I guess it's been around for about 2 years now, but it works pretty well. So we're happy to sort of introduce you guys to it. So the way standalone kind of works, so if you just write faucet config without turning on stacking, you will get standalone mode. So everything's going to happen per switch. So the pros of this is it's really, really simple. It's if you write the first simplest thing, this is how you write it. And it's kind of, I guess, expected behavior for a switch. So traditional switches, Faucet in traditional standalone mode, they look pretty similar. The cons, though, so we don't get this utopia of SDN. So we don't get this full network topology information. We don't get this full fabric that we can sort of make smart decisions about stuff in the context of the whole network. So that's kind of why we came up with something different. And so another con of standalone mode is building like a loop-free network is quite difficult. So we want loops on our network for redundancy for devices and cables, but we can't really have it in standalone Faucet mode without an SDP-like protocol. And I know there's no way Josh would ever merge an SDP protocol into Faucet. So we have to come up with some other way. You could, yeah. So yeah, I'll get into a little bit about how this happens at L2 and L3. So, so the way you can think of Faucet in standalone mode in terms of the code, this is very, 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 very simple and high level. But basically, we get these kind of valve objects, and a valve object implements behavior. So it's a bunch of Python code. It has functions like learn, host, and stuff like that. And this is where all kind of routing happens. It's where ACLs are built, that kind of thing. So in standalone mode, in each Faucet, it just gets mapped to a data path, and they don't talk to each other. All right. So what do we get in stacked mode? So it's somewhat new. It's got a whole bunch of work this year, which makes it actually quite usable, which is cool. And it kind of lets the whole work act as one big switch or router. So one of my colleagues likes to call these things like swooters. When you kind of go SDN, when you kind of go Faucet, devices end up doing multiple sort of device roles now, whereas previously you kind of had like a switch or a router, or maybe an L3 switch, that kind of thing. And this whole sort of big switch router thing is made up of individual devices that are allowed to come and go as they please. So Faucet tracks the entire network topology, and it's making decisions now in context of that. So the pros are, so we can easily build loop-free topologies because we know the network topology. We can easily recover from failure scenarios as long as we can detect them. And there's a whole lot less configuration required because Faucet will just go, I see that's a VLAN trunk. Let me put the VLANs that need to be on that trunk for you, and you don't need to configure it anymore. So, we can't have everything for free. So the cons of this, so we have to do a little bit more work. It's not too much more work, but we do actually have to do some more work to make this work. And if you kind of look at a switch now, you look at a flow table, it's not immediately obvious what that switch is doing anymore because it might be shunting some flows to another switch to do part of the work. So those are kind of the obvious downsides. So how you can sort of think of this, and this isn't a complete picture, this is very simplified, but we have a coordination thing in Faucet now that lets switches know about each other, and it sort of tracks a topology. So how does it work kind of like at a code level? So there's this great thing in Python called NetworkX, and it's a graph data structure. So we basically feed it in a network topology. So we feed it in the one that you tell us in the Faucet YAML. And we also use, actually, that's another slide. But so we feed in the config into NetworkX and we construct a graph. So a graph has a few things. So it has a root. So we pick a root of the network, just like you do for spinning tree. It has data paths, so your switches. Those become the nodes in the graph. And we also have these new things called stack links. And these become the edges of our graph. And then we can run a bunch of algorithms on this graph, like shortest path, and we can make the network sort of have these loop-free topologies based on that shortest path. Yep. So stacking's built to be modular from a code point of view. So we have a number of different stack algorithms for detecting healthiness of the stack, healthiness of links. For different topologies, we'll do different things with learning and flooding. So that's so that we can enable users to build a whole bunch of different topologies, but all kind of roughly based on the same code and same code base. So we never wanted to sort of prescribe to everyone, this is the canonical Faucet stack. We want you to go and play with weird topologies. If they don't work fully optimally, you can throw in some code that is an extra algorithm that sort of treats the traffic a bit differently. So one example of the modularity is in the stack flooding. So we need to be careful with how we flood broadcast traffic in a stack, because you might have redundant links, you might have loops around the network. And so we've got two very, very, very simple algorithms right now for handling flooding. So we calculate the sort of shortest path, and we either have a no reflection or a reflection version of a flood. So in the reflection case, it's pretty simple. You just send all the flooded traffic to the root of the network, and then that knows how to get to the rest of the network. So that's not fully optimal, and we have some more optimal algorithms to come, but this is just to say that we need to handle broadcast traffic in a smart way so that we don't have loops. Okay, so when you turn on stacking, you get a whole bunch of stuff for free, which is quite nice. So you get cable verification and link testing. So when we boot up a stack, so you tell us the topology with the Faucet YAML, and then what Faucet does is it sends LLDP messages around every stack link on the network, and it makes sure everything's plugged in properly, which is quite nice because pretty much every time I bring up a stack, I have at least one cable wrong, if not all of them. Because I don't know, there's just so many little places you can put the cables, and if they're all in one rack, they're so close to each other. I don't know. Maybe I'm just a terrible human being, and maybe you guys get it perfect every time, but I definitely don't. And the other nice thing about this is you can use this to work out if your stack links are working as well. You might have an SFP failure, you might have a fiber failure. This lets you do sort of both. So yeah, going back to it makes your config simpler. So we get this automatic VLAN expression now. So on stack links, we sort of look down the stack from, when we're looking at an individual stack link, we look at all the switches down that stack and up that stack. We work out which VLANs need to be expressed on that link. And so you don't have to do that anymore, which makes your config a lot simpler and shorter, and it doesn't need to change as much as it did before. So if you add a new VLAN, you can pretty much just add it to where it needs to go, and Faucet does the rest. Now, I don't know about you guys who have worked on traditional networks, but I always found configuring VLANs was the hardest part, because you always miss a switch, or you might have some VTP database thing, and then it goes off to your network might go through like a different vendor gear that doesn't support that, and then you got to remember to build all your VLANs there. So this is quite nice to not have to do that anymore. So with stacking, so the kind of primary reason for it is failover. So there's a couple of things that can die on a network, especially a Faucet one. There are links that can die, and there are switches or routes that can die. So we have the ability to have multiple of those now. And then another funky thing we have is this thing called tunneling. So what tunneling lets us do is so I call it packet teleportation, because you can kind of say, I've got these packets over here on this switch, on this port. I want them to go to this switch and this port. and Faucet will use the shortest path to work out where that tunnel needs to go. It builds it for you. If the topology changes, it'll reroute that tunnel for you, assuming that there is another route it can go, which is also quite handy for some things. Okay, so let's start with the very simplest stack topology you can build. And here, I apologize for my graphs that are confusing, but I will try and explain them. So what we've got here is we've got 2 switches and we have a stack link. So this is the simplest possible stack you can build. You can't build one out of one because that doesn't make sense. And in this case, we would have a root. So we'd have switch 1 as our root and switch 2 is our edge. And then they've both got a single VLAN on it with a host on each. So how would we build this? Okay, so this is the entire config for that network. And we'll notice we've introduced a few different pieces of config that you might not have seen before if you haven't configured a stack before. So we kind of have this stack priority value. And so you put that on a root switch. If you have multiple root switches, you put that on multiple switches. And that sort of indicates to Faucet, hey, I want you to start the graph here. And then you basically say for each switch in the stack, how they're linked. So on switch 1, we'll see port 2 is a stack link, and it goes to switch 2, port 2. That's how we can do the cable verification, because we just send down a specially coded LLDP message on that link, and we make sure that those match. And you'll also notice, so we configure VLANs on the access ports, but we don't have to configure them on the stack ports because Faucet will work that out for you. Okay, now a network of 2 switches isn't always super useful, and having pure simple switching isn't always useful. So now I'm going to run through building some more interesting things. So inter-VLAN routing, tunneling, and some resilient network designs. Okay, so this goes back to the question I had yesterday evening. So inter-VLAN routing. So how it works before stacking is you have a single switch, you have multiple VLANs on that switch in different networks. You give Faucet some VIPs, you put your hosts in different subnets, and you go, I want these VLANs to be able to route, and Faucet allows them to route. So the way you do this, so you define a MAC address and a virtual IP on each VLAN, and then you define a router object and say which VLANs can talk, and Faucet will do the rest for you. So that's how it works on a single switch. And the often complaint we got, I think we got up to probably something like 10 feature requests for this, and we kind of figured maybe we should write this. So now we have multi-data path into VLAN routing. Now I know that's a mouthful, but that's kind of what it ends up being. And so now what we can do is we can have a copy of that switch 1 and have another switch 2 with the same sort of VLAN structure on it, or it can be a different VLAN structure, it doesn't matter. And you can have stack link between there, and now Faucet will automatically work out all the routes where they need to be and do that all for you. All you have to do is put that router statement in there, and Faucet does the rest. So this is how we built the Plugfest topology on Monday. We had basically a stack root and a bunch of edge switches, and we just randomly plugged the internet into one of those switches, and we told Faucet, here's a WAN subnet, here's where it is, here's the next hop, figure that out. Here's the default route, and it put that on all the switches for us. We didn't require any configuration, and then suddenly everything on the whole network had internet. So this turns out to be quite a powerful thing. Just based on how little you have to do to configure it, you kind of just get it for free. Okay, so now let's talk a little bit about tunneling. So as I said before, we can automatically stitch a tunnel over a stack topology. And the mechanism we've picked to do that is ACLs. And so you basically have an ACL that matches some subset of traffic, and you say, I want this to go somewhere else, and Faucet works that out for you. Okay, so how do we build that? So here's a bit of an example. So along the top, we have our ACL. So for those that haven't seen ACLs in Faucet before, so we normally have a match, and then we have an action or a set of actions. And Faucet will compile those down kind of to a single rule. Sometimes it'll be multiple rules, but it's mostly OpenFlow-like. except in the actions is where we get a bit tricky. We have a bunch of synthetic actions that we make that aren't available in OpenFlow that let you do cool things. And so because this rule we've made doesn't have a match, it's going to match all packets. And what we do is we apply this as a port ACL to port 1 on switch 1, and we say tunnel to host 2. And that means we'll match everything on that port to this ACL. And then what the ACL does, so we have this new tunnel type output. So normally output was used for, I want to output to this port on the switch I'm currently on, but now we've extended it to this tunnel thing. And you put the type of tunnel. So at the moment we only support VLAN, and that's just mostly because that was the easiest way to test on all vendors, because everyone can do VLANs. Though in future we'd love to obviously do MPLS or Q&Q, that kind of thing. And all the configs there ready to let you do that. It's just we haven't wired in the back end yet. And then what you do is you give it a tunnel ID. So for VLAN, that's going to be the VLAN ID. You just have to make sure not to reuse that for something else. Or maybe you would use it for something else, and then you're just telling this to jump it into another VLAN, who knows. And then you say, where should that packet go? So you say here, I just say go to switch 3, completely ignore switch 2 ever exists. And then the packets will just tunnel. So a unidirectional tunnel might not be the most useful thing. So if you want to do it both directions, you just add another one saying come back. And now you've got end-to-end connectivity between two hosts, completely bypassing all VLAN restrictions and all whatever. And so you can think of a number of different ways this might be useful for talking out to remote things on the network, and you could have multiple of them and just stitch up tunnels as you need to. And because it only matches on a subset of traffic, you can start to send sort of individual protocols to different machines on your network. It's going to be 902, so that's what the tunnel ID is. So it's kind of outside of forwarding and Faucet.
You will translate the 902 by name.
Yep. Yep.
So mirroring is also an action. Is there a way to mirror to a tunnel?
Yep. Yep. So Charlie and Josh have done that in production, I think, even. Or testing. We have a proof of concept that works, but we'll make it easier. I believe at the moment it requires a loopback cable, but we'll work on that. Yeah. Yeah. But I played with that as well. Okay. Anything else on tunneling? No, cool. So resiliency. So stacking, so it solves one resiliency problem at the cost of introducing another. So we can do loop-free topologies, we can build these great big things now, but as I said, we always need a route to calculate the shortest path. So I mean, the simplest way to solve this is you just add another route, and that's how we solved it. So you can indicate multiple routes now. So what does that let us do? Well, it lets us build topologies like this. So this is kind of like a spine and leaf type thing, Cowie network. So we've got sort of two switches along the top now, and they're both set stack priority 1, which means they're both candidates to be a route. And Faucet has a number of different algorithms for picking which route it wants to use, and it can detect when a route goes away, and it can change to another candidate. And so then we kind of end up with these sort of access switches down the bottom that they can lose one of these uplink switches or some of these cables, and the network keeps working. So, and you might see the title. I call this bulletproof Faucet. The idea with you can take a gun with a single bullet, shoot something, and it should keep working. So how does this work when you've got it all configured? So by default, sort of, so if we assume switch 1 gets selected as the route, so your traffic flow will look like this to start off with between host 1 and host 2. And what we can do is, so we can survive a cable failure. So if we lost this cable, so Faucet will automatically reroute your traffic between these two hosts this way. It can survive a switch failure. So in this case, we lose a switch, but we also lose all links on that switch when the switch goes down. So there's still a valid path through the network. So Faucet will send all the traffic that way. Eventually, they'll get to a point where you run out of valid links and things can't talk, but Faucet will make it work as long as there's valid path through the network. So I think at the moment we check every 30 seconds for a switch stack failure, sorry, a root failure. But you can configure it to whatever you accept. So obviously the trade-off there is you don't want to have this kind of soft failure where you're flapping your route. So we have this hard-coded time value where it's only every 30 seconds that we would try and move traffic. But as I said, all this is modular. You decide on what's your appetite for failure, like how long do you want it to take before it starts working again. But we find most people in sort of the enterprise space, as long as it comes back quicker than it would take for someone to run up and retake some cables, that's quite nice. Obviously, this isn't going to work in a telco scenario where you need 50 milliseconds failover, but for the enterprise environment, it's quite good. Okay, so if you want to try stacking out yourself, so I've, in the last couple of weeks, written a whole new tutorial series on stacking, and yeah, it's I think it's quite fun because you can basically chain all these kind of things together and build some kind of wacky weird network. I've built a lot of weird ones in my testing. My favorite was the cheese wedge network, which is a triangle. So you can build rings with this. You can build spinal leaf type things. We haven't really limited it to particular topologies. We'd love for you guys to go off and try some other weird topologies and tell us if it works or not. So yeah, if you go through the tutorial, it's at that URL, or just go to docs.faucet.nz, click tutorials. You'll configure in a virtual environment everything I've talked about today here and prove it works with some pings and stuff. I've done it a couple of times and I can tell you it works, but if it doesn't work, please let me know and we can go fix something. And just a final slide to say thanks. So I've mostly been introducing work that is not my own. So Josh did all the original stacking work. He made multi-route work for us recently. He's fixed a number of bugs in various different topologies. And then a thank you to Mab68. I sure got a shout out yesterday. So he's actually one of our students, and he's very, very capable and puts out a lot of good code. So he did the inter-VLAN routing work between multiple switches, and he also made tunneling work. So yeah, I'll shout out to him as well. And I always send your thanks to him, and he appreciates it. He likes it. Any sort of questions? Yeah, so we're kind of, I guess the direction for Faucet we're going is we prefer you guys to use this sort of stack thing because it just makes our lives so much easier. So Josh calls it spanningless spanning tree. So it's a spanning tree that converges instantly because we have all knowledge of the network instantly. So that's the benefit over distributed spanning tree.
We're using the spanning tree.
So this is, once again, that kind of SDN utopia, right? We know the topology, so we can do things faster than everyone else.
And also, yeah, a place like this, the idea that
Bob? Yep.
I think that's your bulletproof Faucet example. It's fine. So in this configuration, are you using one thing that always made me sad about spanning tree is you're throwing away useful capacity. So in this example, can you use both of the uplinks and downlinks?
So I think.
Or do we only use sort of do it at some point in time?
So I think for broadcast traffic, we'll only use one part, and then for host to host, we can probably discover multiple parts.
We can. There's lots of optimization.
Yeah.
So yeah, I don't fully utilize.
I guess if it doesn't today, could we just just use like okay, the stack acts as a virtual switch. Basically, use lag to work with the
Yeah, so I went for simple examples here, but we do have another deployment where we have this type of network and you do LACP out the top to another network and you can load balance there. So, but yeah, as Josh said, this is southbound. Oh, sure.
Where you basically stack the upper together, the lower one, basically aggregate the two.
So we tried that on Riskager last Friday, and there were some issues with math learning.
Yeah.
But it bugs to be solved. But we had a lag coming from the host, but it was going one link was going to switch 2, and one link was going to switch 1.
Yeah.
Yeah, I think we've got a bug there, but we're quite keen to fix that one because that's a really cool use case.
Yeah, that's awesome.
Yeah.
So if you do stop training, maybe this is simple optimization. That would take. Anything else is won't work.
I actually think the work that somebody contributes code is I harbor shame on having we cannot deploy full that I feel is actually not constructive. Do you really need to use both links? I'm not saying that not using all available to you is a good thing, but having a network that's reliable and for me
There are a couple of, like, to your point about VLAN, so there's other bunch of to-dos. One to-do is free. It's a case where you can have multiple, say, balance them by, or you can use the bucket abstraction to say, nice people can help you which level with the hardware and
Yeah, but
you triggering on events. Link get the link down event and then instantly.
yeah, so OpenFlow has this great sort of event system, so it can tell you this port is hard down right now, and we instantly recognize that. And then for the LACP stuff, I think we send them every 15, 5, 10 seconds, something like that, and you need to lose 3 or something, and then we declare it being a soft failure and the link shouldn't be used anymore. Something like that.
The idea is like some number
in it. Yeah. So we check for both. Yeah, actually. Yeah. Simply. So we accept packets on both and we send on one. So we assume the other end does all the load balancing. But yeah, there are smarter things you could do. We just don't do them yet. Cool. Anything else? All right. Thank you.